Hello, this is my English speaking practice, and I'm talking about my personal, my tech study. Yep, but it seems that the network connectivity is not good. But I don't care because I think there is no one watching this stream. Okay, so I will continue this one. And yeah, I learned core concepts yesterday, and I left off here locking. So let's get started. In our system, we may have shared resources which can only be accessed by one client at a time. An example might be shared counter like inventory units or an interface to physical devices. Drawbridge app. I don't know. Locking is a process of ensuring that only one client can access a shared resource at a time. Locks happen at every scale of computer systems. There are locks in your operating system's kernel, locks in your applications, locks in the database, and even distributed locks. Hence, they are a common topic in system design interview. Locks are important for enforcing the correctness of our system, but can be disastrous for performance. Yeah, I agree. In most system design interviews, you will be forced to contend. You will be forced to contend with locks when you consider race conditions. A race condition, if you remember, is a situation where multiple clients are trying to access the same resource at the same time. This can lead to data corruption, lost updates, and other bad things. There are three things to worry about when employing locks. Granularity. The quality or condition of being granular. Technical. The scale or level of detail present in a set of data and other. 流度ね。グラニュー糖とかのグラニュー。Okay, granularity of the rocks. Makes sense. We want rocks to be as fine-grained as possible. This means that we want to lock as little as possible to ensure that we are not blocking other clients from accessing the system. For example, if you are updating a user profile, we want to lock only that user's profile and not the entire user table. Duration of the lock. We want locks to be held for as short a time as possible. This means that we want to lock only for the duration of the critical section. For example, if we are updating a user's profile, we want to lock only for the duration of the update and not for the entire request. Whether we can bypass a lock. In many cases, we can avoid locking by employing an optimistic concurrency control strategy, especially if the work to be done is either read-only or can be retried. In an optimistic strategy, we are going to assume that we can do the work without locking and then check to see if we were right. In most systems, we can use a compare and swap operation to do this. Optimistic concurrency control makes the assumption that most of the time we won't have contentions contention or multiple people trying to lock at the same time in a system, which is a good assumption for many systems. That said, not all systems can use optimistic concurrency control. For example, if you are updating a user's bank account balance, you can't just assume that you can do the update without locking. Read concurrent record version and check version mismatch, handle conflict. Same version, process record update, write new version, end. Okay. I'm interested in locking, or like that. Yeah. So this article is very nice. Indexing is about making data faster to query. In many systems, we can tolerate slow writes, but we can't tolerate slow reads. Indexing is the process of creating a data structure that makes reads faster. The most basic method of indexing is simply keeping our data in a hash map by a specific key. When we need to grab data by that key, we can do so in Omicron 1 time. Suddenly, we don't need to scan the entire dataset to find the data we need. Another way of the indexing is to keep our data in a sorted list. This sorted list. This allows us to do binary search to find the data we need in Omicron log n time. This is a common way of indexing data in database. There are many different types of indexing, but the principle is the same. Do a minimum amount of upfront work so that your reads can be extra fast. Indexing in databases. Most questions of indexing will happen inside your database. Depending on your database choice, you will have different options for indexing. For example, most relational databases allow you to create indexes on any column or group of columns in a table. This isn't unbounded, however. This isn't unbounded, however. Unbounded isn't unbounded. Yeah. While databases like DynamoDB allow you to create many secondary indexes for databases like Redis. While databases like DynamoDB allow you to create many secondary indexes, for databases like Redis, you are on your own to design and implement your own indexing strategy. If you can do your indexing in your primary database, do it. Databases have been honed over decades for exactly this problem, so don't reinvent the wheel unless you have to. Okay, so this means maybe the databases have been developed contention or So I mean, databases have been developed by mm, many developers in order to handle the indexing problems. Yeah, mm, so you don't need to reinvent reinvent the wheel. Uh, so you don't need to make it by yourself. Okay, that makes sense. And specialized indexes, in addition to the basic index strategies, there are many specialized indexes that are used to solve specific problems. For example, geospatial indexes are used to index location data. This is useful for systems that need to do things like find the nearest restaurant or the nearest gas station. Vector databases are used to index high-dimensional data. This is useful for systems that need to do things like find similar images or similar documents. And full text indexes are used to index text data. This is useful for systems that need to do things like search for documents or search for tweets. Many mature databases like Postgres support extensions that allow you to create specialized indexes. For example, Postgres has a PostGIS extension that allows you to create geospatial indexes. If not, you will need to maintain your indexes externally. Elasticsearch is our recommended solution for these secondary indexes when it can work. Elasticsearch supports full text indexes search by text via Lucene geospatial indexes, and even vector indexes. You can set up Elasticsearch to index most databases via change data capture CDC, where the ES cluster is listening to change coming from the database and updating its indexes accordingly. This isn't a perfect solution. By using CDC, you are introducing a new point of failure and a new source of latency. The data readout of your search index. The data read out of your search index is going to be stale, but that might be okay. It's very common for candidates to introduce Elasticsearch as a potential solution to their problem without understanding its limitations or explaining how it's used. Make sure you brush up on the fundamentals so that you're ready on interview day. Communication protocols. Protocols are an important part of software engineering, but most system design interviews won't cover the full OSI model. Instead, you will be asked to reason about the communication protocols you will use to build your system. You've got two different categories of protocols to handle: internal and external. Internally, for a typical microservice application which contributes 90% above 90% or more of system design problems, either HTTPS or gRPC will do the job. Don't make things complicated. Externally, you will need to consider how your you will need to consider how your clients sorry, okay. Externally, you will need to consider how your clients will communicate with your system. Who who initiates the communication? What are the latency considerations and how much data needs to be sent? Across choices among most systems can be built with a combination of HTTP, SSE, or long polling and WebSockets. Browsers, browsers and apps are built to handle these protocols and they are easy to use. And generally speaking, most system design interviews don't deal with clients that need to have custom high performance protocols. Server sent events bidirectional channel. Huh. Okay. Use HTTP for APIs with simple requests and responses because each request is stateless. You can scale your API horizontally by placing it behind a load balancer. Make sure that your services aren't assuming dependencies on the state of the client, and you are good to go. If you need to give your client near real-time updates, you will need a way for clients to receive updates from the server. Long polling is a great way to do that blends the simplicity and scalability of HTTP with the real-time updates of sockets. With long polling, the client makes a request to the server and the server holds the request open until it has new data to send to the client. Once the data is sent, the client makes another request and the process repeats. Notably, you can use standard load balancers and firewall with long polling, no special infrastructure needed. WebSockets are necessary. WebSockets are necessary if you need real-time bidirectional communication between the client and the server. For a system design perspective, WebSockets can be challenging because you need to maintain the connection between client and the server. This can be a challenge for load balancers and firewalls, and it can be a challenge for your server to maintain many open connections. A common pattern in these instances is to use a message broker to handle the communication between the client and the server, and for the backend servers to communicate with this message broker. And this ensures you don't need to maintain long connections to every service in your backend. Lastly, server sent events (SSE) are a great way to send updates from the server to the client. They are similar to long polling, but they are more efficient for an unidirectional communication from the server to the client. SSE allows the server to push updates to the client whenever new data is available, without the client having to make repeated requests as in long polling. This is achieved through a single long-lived HTTP connection, making it more suitable for scenarios where the server frequently updates data that need to be sent to the client. Unlike WebSocket, SSE is designed specifically for server-to-client communication and does not support client-to-server messaging. This makes SSE simpler to implement and integrate into existing HTTP infrastructure, such as load balancers and firewalls, without a need for special handling. Statefulness is a major source of complexity for systems. Where possible, relegating your state to a message broker or a database is a great way to simplify your system. This enables your services to be stateless and horizontally scalable while still maintaining stable connections. Okay. Okay, next. Security. When designing production systems, security should be top of mind. While system design interviews are rarely going to require you to do dedicated security testing of your design, they are looking for you to emphasize security where appropriate. This means that you should be prepared to discuss how you will secure your system at every level. Some of the most common security concerns are authentication and authorization. In many systems, you will expose an API to external users, which needs to be locked down to only specific users. Delegating this work to either an API gateway or a dedicated service like Auth0 is a great way to ensure that you are not reinventing the wheel. Your interviewer may want you to discuss the finer details like how specific entities are secured, but often it's sufficient to say my API gateway will handle authentication and authorization. Okay, encryption. Once you're handling sensitive data, it's important to make sure you're keeping it from snooping eyes. You will want to cover both the data in transit and the data at rest. HTTPS is the SSL/TLS protocol that encrypts data in transit and is the standard for web traffic. If you are using gRPC, it supports SSL/TLS out of the box. For data at the rest, you will want to use a database that supports encryption or encrypt the data yourself before storing it. For sensitive data, it can often be useful. For sensitive data, it can often be useful for the end user to control the keys. It can often be useful for the end user. Yeah, this is a common pattern in systems that need to store sensitive data. For example, if you are building a system that stores user data, you might want to encrypt the data with a key that's unique to each user. This way, even if your database is compromised, the data is still secure. Data protection. Data protection is the process of ensuring that data is protected from unauthorized access, use, or disclosure. Frequently, production systems are concerned with data that's sensitive when exposed, but might not be within an authorization path. Example, a user's data might be exposed via create friend request endpoint. Many exposures of this sort are discovered by scraping endpoints, so having some sort of rate limiting or request throttling is a good idea. Last topic, monitoring. Once you've designed your system, some interviewers will ask you to discuss how you will monitor it. The idea here is simple. Candidates who understand monitoring are more likely to have experience with actual system in production. Monitoring real systems is also a great way to learn about how systems actually scale and break. Monitoring generally occurs at 3 levels, and it's useful to name them. Infrastructure monitoring is the process of monitoring the health and performance of your infrastructure. This includes things like CPU usage, memory usage, disk usage, and network usage. This is often done with a tool like Datadog or New Relic, where a disk usage alarm may not break down your service. It's usually a leading indicator of problems that need to be addressed. Service level monitoring. Service level monitoring is the process of monitoring the health and performance of your services. This includes things like request latency, error rates, and throughput. If your service is taking too long to respond to requests, it's likely that your users are having a bad time. If throughput is spiking, it may be that you are handling more traffic or your system may be misbehaving. Application level monitoring is the process of monitoring the health and performance of your application. This includes things like the number of users and the number of active sessions and the number of active connections. This could also include key business metrics for the business. This is often done with a tool like Google Analytics or Mixpanel. This is often the most important level of monitoring for product design interviews. Okay, I've learned core concept. So, let's move on to key technologies. Core database, blob storage, search optimized database, API gateway, load balancer, queue, streams, distributed log. Okay. Key technologies, and let me see the common patterns. Why not? Okay. Common patterns pushing real-time updates. Okay. Let's go. System design involves assembling the most effective building blocks to solve the problem. So it's crucial to have a good understanding of the most commonly used building blocks. Most interviewers aren't going to care whether you know about a particular queuing solution, so long as you have one you can use. However, let me translate. So long as you have one you can use. Particular. Aren't going to care whether you know about a particular queuing solution, so long as you have one you can use. So long as long as okay. However, if you don't about any queuing solutions, you are going to have a hard time designing a system that requires one. This brings us to our key technologies. In this section, we are going to walk through the key categories of technologies relevant to solving 90% of system design problems, together with some discussion of the possible options for each. You are generally free to choose which technology you want to use in each category. It's category. Each category. You are generally free to choose which technology you want to use in each category. But we recommend you have at least one. Keep in mind that the amount of depth your interviewer is likely to prove is proportional to the level you're interviewing at. At middle level, a middle level candidate who can roughly describe Elasticsearch as a search index is likely to be fine, but a senior candidate who cannot describe the inverted index or the reason about its scaling is likely to be yellow flag. In either case, focus on breadth before depth. Breadth before depth. Yeah. So it's important to have a wide knowledge. Core database. Almost all system design problems will require you to store some data, and you're most likely going to be storing it in a database or a blob storage. While there are many different types of databases, the most common are relational database, example Postgres, and NoSQL as databases, example Dynamo database. We recommend you pick one of these for your interview. If you're taking predominantly product design interviews, we recommend you pick a relational database. If you're taking predominantly infrastructure design interviews, we recommend you pick a NoSQL database. Many candidates trip themselves up by trying to insert a comparison of relational and NoSQL databases into their answers. The reality is that these two technologies are highly overlapped, and broad statement like I need to use a relational database because I have a relationship in my data. NoSQL databases can work great for this, or I've got to use NoSQL because I need scale and performance. Relational databases, used correctly, perform and scale incredibly well, are often yellow flags that reveal inexperience. Okay, here's the truth. Most interviewers don't need an explicit comparison of SQL and non-SQL databases in your session, and it's a pothole. It's a pothole you should completely avoid. Instead, talk about what you know about the database you're using and how it will help you solve the problem at hand. If you're asked to compare, focus on the differences in the databases you're familiar with and how they would impact your design. So I'm using Postgres here because its ACID properties will allow me to maintain data integrity. Is a great opener. Okay. What is a relational database and when you should use it? When should you use it? Relational databases, sometimes called RDBMS or relational database management systems, are the most common type of database. They are often used for transactional data, user records, order records, etc., and are typically the default choice for a product design interview. Relational databases store your data in tables which are composed of rows and columns. Each row represents a single record and each column represents a single field on that record. For example, a user's table might have a name column and an email column. Relational databases are often queried using SQL, a declarative language for querying data. This is fundamental, and learning how RDBMS to work and the cover is behind the scope of this guide, but we recommend you read a deep dive into how databases work if you're interested in learning more. Understanding how data flows internally through a database is a microcosm of the tricks you can use in your system design interview to optimize for performance and scale. Things you should know about relational databases. Beyond simply storing data, relational databases come equipped with several features which are useful for system design interviews. The most important of these are SQL joins. Joins are the way of combining data from multiple tables. For example, if you have a user's table and a post table, you might want to query for all posts by a particular user. This is important for query data and SQL databases and can support arbitrary joins between tables. Note that joins can also be a major performance bottleneck in your system, so minimize them where possible. Where possible. Minimize them where possible. Indexes. Indexes are a way of storing data in a way that makes it faster to query. For example, if you have a user's table with a name column, you might create an index on the name column. This would allow you to query for users by name much faster than if you didn't have an index. Indexes are often implemented using a B tree or a hash table. The great thing about relational databases is their support for arbitrarily many indexes, which allows you to optimize for different queries, and their support for multi-column and specialized indexes like geospatial indexes, full text indexes. RDBMS transactions are a way of grouping multiple operations together into a single atomic operation. For example, if you have a users table and a post table, you might want to create a new user and new post for that user at the same time. If you do this in a transaction, either both operations will succeed or both will fail. This ensures you don't have invalid data like a post from a user who doesn't exist. What are the most common relational databases? The most common relational databases are Postgres and MySQL. If you don't already have a favorite, we recommend you pick Postgres, and we have a great deep dive to help you with the details, but either one is fine. Okay, I get tired, so let me wrap it up. Hello. I'm gonna talk about what I've learned today. First, I've learned about locking. Locking is important concepts in system design. And the article says there are 3 types of things to consider. First, granularity of the logs. Because the log may cause the long latency or like that, so the log granularity should be small. Yeah, so we should minimize the granularity of the logs. And second, about duration of the logs. This is similar to granularity of the logs. So we should minimize the duration of the logs. Mm. I didn't. I didn't understand it this well. Um, so we should avoid the lock if if possible, right? Hmm. Optimistic concurrency control. Third, we should avoid the lock if possible. So we can use an optimistic concurrency control. But honestly, I didn't understand it well. The article says in many cases we can use compare and swap, which I think which is the CPU operation, CPU atomic operations. So yeah, it can provide us control for concurrency. So I, in my understanding, if we can avoid using locks by CPU atomic operations, we should do that. Indexing, communication protocols, security, encryption. Okay, but today I've I've been tired, so let's finish. But before finishing, I have AI review it. So I'm going to talk about what I learned today. First, I learned about locks, which are important concepts in system design. The article says there are three main things to consider: granularity of the lock. Locks can introduce latency, so the granularity should be small. In other words, we should minimize the scope of the lock to reduce blocking. Avoiding locks if possible. Whenever we can, we should avoid using locks. One approach is optimistic concurrency control, though I don't fully understand it yet. The article also mentions that in many cases we can use compare and swap, which is an atomic CPU operation. My understanding is that if we can avoid using logs by using CPU to make operations, we should do that. Yeah. Polish version. Okay. So, thank you for watching. See you.